our claim is that a simple function is measurable if and only if each one of the ai's belong to S. So, we want to prove a simple function S, which is sigma ai, indicator function of ai I equal to 1. We want to show that this is measurable if and only if. Let us observe. So, note, to check measurability, we have to look at f inverse of an interval I. So, what is that going to be? That is, the function S takes values ai's, small ai's on the set ai. So, this is the main thing to be observed, that a finite linear combination of the indicator functions is a function which takes only finite number of values, namely a 1, a 2, a n, and the value small a I is taken on the set capital A I. So, what will be S inverse of I? That will be union of those sets A I, union over I says that A I belongs to the interval I, right. So, clear. So, let us once again observe that S takes values a 1, a 2, a n. So, look at the inverse image of an interval I. So, look at those i's, say that a I belongs to I, the interval I. So, this will, the pullback of this will be the set a I. So, look at the unions of these a I. So, S inverse of I is union of a i's, right. So, if each a I belongs to S for every I, this will imply that S inverse of intervals belong to S. So, implies that S is measurable, because the inverse image of every interval belongs to I, and this interval is in the extended real numbers. So, plus infinity and minus infinity are included in this. So, is measurable, and conversely, if S is measurable, then look at S inverse of singleton A I. So, that will be equal to A I, and hence measurability implies this belongs to S. And of course, here a slight care one has to take. We can assume that all the AIs are distinct, okay? Because if they are not distinct, we can put together those AIs into one box. So, that leads to our, so anyway, so that says that a simple function is measurable if and only if all the sets involved in the representation as A I times chi of A I are all measurable. So, as observed just now, they have given a simple function S, we can also write it in the form, we can represent as A I summation A I indicator function of A I, where all the A I's are distinct and these capital A I's are disjoint. Because if sets are not disjoint, we can put them together. If the same value is taken on two distinct sets, then we can put them together in one box and call that set as a new A I. So, this is sometimes called a standard representation of a simple function, where the AI's are all distinct and this capital AI's form a partition of the whole space X. So, a simple function is nothing but a finite linear combination of indicator functions. So, that is example of measurable function. We will study some more properties of these simple functions or this class of simple measurable functions. So, let us start with S, S1 and S2 be simple measurable functions and alpha is a real number. So, first of all we want to observe that every constant function is a simple measurable function. What is a constant function? A constant function is nothing but a function which takes a single value everywhere on the set. So, we can think it as if the constant value is taken is C, then it is C times the indicator function of the whole space X. So, every constant function is simple measurable, because it is a constant multiple of indicator function. Say alpha times a simple function is also a simple measurable function, because because of the fact that if a simple function s is equal to summation a I chi a I equal to 1 to n, then alpha times s is equal to sigma alpha a I times chi of a I equal to 1 to n. So, alpha s is again a simple function and only its values have changed, but the sets on which these values are taken remain the same. So, clearly it indicates that if S is measurable, then alpha S is also a measurable set. The next property we want to check is that if S 1 and S 2 are two simple measurable functions, then S 1 plus S 2 is also a simple measurable function. So, let us take a function S 1, which is sigma a I chi a I 1 to n. So, let us say S 1 has the representation sigma a I chi a I and S 2 has the representation j equal to 1 to m b j chi of b j. Now, whenever one is dealing with more than one simple function, the idea is try to bring the sets involved in the representation to be same. So, here we are assuming that S 1 is a let us say we have a standard representation, then union a I is equal to x and here union b j is also equal to x. Then we can write S 1 as each a I can be decomposed into union of the b j's. So, we can write I equal to 1 to n a I chi of a I intersection b j and union over j's. So, each a I can be intersected with union of b j's. And now, here is a simple fact, a simple observation that the indicator function of disjoint sets. So, here is the observation, if you have two sets A and B and they are disjoint, then A union B is equal to chi of A plus chi of B. So, this we will leave it for you to verify that the indicator function of the union of two sets is equal to sum of the indicator functions whenever the sets are disjoint. So, using that we can write S 1. So, this S 1 can be written as summation I equal to 1 to n a I summation over j equal to 1 to m chi of a I intersection b j. So, this is same as summation over I summation over j a I chi of a I intersection b j. And similarly, for the second simple function S 2, which had the representation b j chi of b j, j equal to 1 to m, we can write this as summation over I summation over j b j chi of a I intersection b j. So, what we are saying is that whenever you are given two or finite number of simple functions, we can assume without loss of generality that the indicator functions involved are of same sets. So, S 1 is equal to summation over I summation over j a I times indicator function of a I times b j indicator function of a I intersection b j, and similarly S 2 can be written as summation over I summation over j b j indicator function of a I. So, then what is S 1 plus S 2? S 1 as plus S 2 is nothing but summation over I summation over j of a I plus b j indicator function of a I intersection b j. And that should be clear, because if I take a point x, then if x belongs to a I intersection b j, then S 1 gives the value a I and S 2 gives the value b j. So, sum will give the value a I plus b j. Outside the value is 0. So, one does not have to bother. So, S 1 plus S 2 can be given the representation sigma summation over I summation over j a I plus b j of this. And now, since a I belong to the sigma algebra, b j's belong to the sigma algebra. So, that implies A I intersection B j is also belong to the sigma algebra. So, S 1 plus S 2 is written as a linear combination of indicator function of sets which are in the sigma algebra. So, that implies S 1 plus S 2 is measurable. Okay. Right. So, this proves the property that the class of simple measurable functions is closed under addition. First property said it is closed under scalar multiplication, this says it is closed under addition. Next, let us take a fixed set, any set E in the sigma algebra and multiply S with the set indicator function of E. Then claim is this is also a simple measurable function, and that comes from a very simple observation. So, let us take a set E belonging to S, and S is a simple function which is sigma A I indicator function of A I. Then S times the indicator function of E is nothing but summation I equal to 1 to n A I indicator function of A I times indicator function of E. So, here is a observation that the product of indicator functions is nothing but the indicator function of the intersection, is nothing but the product of indicator functions is equal to indicator function of the intersected set. So, if we use this, then the set the function S times indicator function of E can be written as sigma A I indicator function of A I intersection E. So, it is again a linear combination of indicator functions of sets A i's intersection E, and since A I belong to the sigma algebra, E belong to the sigma algebra. So, this belongs to the sigma algebra. So, the function S multiplied by the indicator function is a linear combination of characteristic functions of sets which are in the sigma algebra. So, implies S indicator function of E is measurable. So, that proves our next property that, and using this it is easy to check that the product of simple functions is also simple measurable functions is also a simple measurable function. So, for that let us take S 1 is sigma A I indicator function of A I, and S 2 is sigma j equal to 1 to m B j chi of B j. Then S 1 multiplied with S 2 is nothing but we can do distributive law. So, 1 to n A I of chi A I summation B j 1 to m chi of B j. So, we can write this as summation over I 1 to n A I summation over j 1 to m chi of A I chi of B j into that constant B j. So, let us write that B j to be here, right. So, anyway, we need not have done that much. We could have just said that is chi indicator function of A I times S 2, each one of them is simple. So, anyway, this can be written as summation over I 1 to n summation over j equal to 1 to m A I B j chi of A I intersection B j. And so, once again S 1 into S 2 is a linear combination of indicator function of sets where A I belongs to S because S 1 is measurable, B j's belong to the sigma algebra as S because S 2 is measurable. So, intersection is measurable. So, S 1 S 2 is measurable. So, the product of simple measurable functions is again measurable. Let us go a step further and let us define for given two simple functions S 1 and S 2, let us define what is called S 1 maximum of these two functions S 1 V S 2. So, what is S 1 V S 2? This is the function whose value at a point x is defined as the maximum of the numbers S 1 x and S2 x. So, at every point x, compare the values of S1 and S2, whichever is higher, define the value to be that number. So, the claim is S1 V S2 is also a simple measurable function. Once again, the technique is same as for the sum. So, let us write S1 equal to sigma a i chi of a I equal to 1 to n, and let us assume S1 is simple, that means all the a i's are in the sigma algebra S. Similarly, S2 is measurable. So, let us write S2 as j 1 to m and bj chi of bj, where bj's belong to S. And now, we bring them to a common sets as before. So, let us write S1 as sigma over I, sigma over j, a I chi of a I intersection b j, and S2 equal to sigma over I, sigma over j, b j chi of a I intersection b j. Then S1 maximum S2 at any point x. So, we want to define what will be at any point x, the value of this. So, look at a point x, either it will be in one of the sets a I intersection b j, then S1 will give the value a I, S2 will give the value b j, and maximum of that has to be put. So, it is maximum of a I b j if x belongs to a I intersection b j. So, S1 V S2 is nothing but summation over I, summation over j of this. And this is once again a finite linear combination of characteristic function, where the sets involved are in the sigma algebra. So, this will imply S1 wedge S2 belong to S. A similar argument will imply that the corresponding minimum of the two simple function measurable functions is also a measurable function. So, what is the minimum function? So, S1 wedge S2 at a point x is defined as the minimum of S1 x S2 x, that is called the minimum of the two functions, and we want to show that also belongs to is a simple measurable function. So, once again, if S1 is defined as this and S2 is defined as this, then what is S1 wedge S2? So, this can be written as simply sigma over I, sigma over j, minimum of a I b j, indicator function of a I intersection b j. So, once we write it that way, it becomes clear that the minimum also is a, so implies that S1 wedge S2 is a measurable function. Whenever S1 and S2 are a measurable function. So, not only the maximum, the minimum also is a simple measurable function whenever S1 and S2 are measurable functions. And let us finally prove that if S is simple measurable, then mod S is also a simple measurable function. Well, that is there are many ways of looking at this. One can also look at if S is equal to sigma a I chi of a I 1 to n, then what is mod S? Mod S is a function defined at x to be equal to, it is mod of S of x, right. So, mod S is nothing but sigma mod of a I equal to 1 to n indicator function of a I. So, this also is a measurable, because it is if S is measurable, each a I is a measurable set, and mod S is a linear combination of indicator functions of sets which are measurable. At this point, it is worthwhile noting a few things about mod of a function. So, let us take any function f from x to r or r star. Let us look at the function, let us define f plus of x to be a function on x as follows. It is equal to f of x if f of x is greater than or equal to 0, and it is 0 if f of x is less than 0. So, what we are saying is, look at the value of the function f of x. If it is bigger than or equal to 0, then you keep the value of the function as it is. As soon as it goes below, you cut it off by the value 0. So, if this is the function, then f of x, then what is f plus? So, f plus, when it goes below, you keep the value to be 0, because it is going below, because it is up, you keep it as it is. Now, it is going below. So, keep the value to be 0, and now it is going up, right. So, this is the value of, this is the function f plus. So, this is called the positive part of the function. So, this is called the positive part of the function. Similarly, we can define what is called the negative part of the function to be as follows. So, given a function f from x to r star, the negative part of the function f of x is defined as 0 if f of x is bigger than 0. As soon as it becomes positive, we make it 0, and we make it equal to minus of f of x if f of x is less than or equal to 0. Keep in mind the negative. So, what it says, look at, if this is the graph of the function, then what do? We look at the graph. As soon as it is below, we keep it as it is. When it is going above, when it is 0 if f is positive. So, on the positive part we keep it here. When it is below, we reflect it up. So, it is this, and this, and so on. So, note that, so this is called the negative part of f. So, let us observe the function f is written as the positive part minus the negative part. Every function can be represented as the positive part and the negative part, and both these functions are non-negative functions, and mod of f can be written as f plus f minus. So, that is the mod f. You can also think of the positive part f plus can be also thought of as the maximum of f and the function constant function 0, and f minus can be thought as maximum of minus f and 0. So, another ways of looking at it. So, if for a simple function saying that mod f is measurable can also be looked at, because if s is measurable, simple function is measurable, the maximum of simple function and 0 is measurable, the positive part is measurable, the negative part is measurable, and hence mod f will be also measurable. So, we will continue properties of measurable functions in our next lecture. In the next lecture, we will prove an important theorem, namely we will look at how sequences of measurable functions behave, whether the limits of sequences of measurable functions are measurable or not. Thank you.